Thank you very much. It's quite an honor to be here. What I'm going to present, the original research is made by 3 people, which I just the one that make it to here. It's not that the other 2 got lost, it's just they couldn't make it. So what we started as a profiling exercise ended up to be a tool that we released, and we're going to show it how actually we started from doing DNA malware profiling to actual building a full-fledged tool to be able to achieve that. So when we started with this research, we kind of knew that we are going to encounter a few things that is going to be quite complicated. We have in terms of issues for malware hunters, malware researchers, there's a lot of code that is being obfuscated, transformed, or being manipulated in a way that makes malware researchers make the work quite difficult. In terms of data, in terms of data obfuscation techniques, in terms of trying to evade detection from antivirus companies, right? So and then also we have polymorphic code and stuff like that. So we kind of knew that we are it's going to be quite complicated to achieve something like this, to do actual profiling or clustering of malware, right? And on the other hand, in the past there was I would say it was easier to actually detect malware because it was often very expensive to compute CPU time to build a new version of a new version of the malware. So these days CPU time is meaningless, the cost. So builders these days build the malware file, executable, whatever it is, macro, whatever, for each interaction, for each time it needs to be launched, right? So on that we have a note here from the Verizon analysis of that data breach that they profile 40 million malware records, and out of through multiple companies, and out of that they only found 20,000 hashes that were present in multiple companies. That means the majority of them are actually unique, right? So we kind of knew that. But we still do picture the problem here, and then we encounter with stuff like this, where a lot of antivirus company put a lot of detailed reports where it's actually for not so deep techie heavy people to understand what it means, all this data, and not like an easy way to represent that data, because at the end of the report you're reading, and this is from Tuku, from the people from Kaspersky. This it doesn't make too much sense when you read that. Well, you see something that looks like a SQL, and then you have IPIs there and some DL name, but it's actually difficult to have meaningful information out of those if you don't fully understand the whole picture, right? That also make complicated, signature and heuristics-based detection on those things that you see in those reports. So they put a lot of detail, and at the very end they give you just a bunch of hashes, and that's it. So it's like something. There needs to be something in the middle, right? So that's where we say those are the remainings of the gap. When you see a report, you read some from Symantec for whatever company, and at the very end you just put in a bunch of hashes, and it's like all diluted, the information that you can action on top of those, right? So example of that is that we'll still read those reports, and you see the specific things that you have out of those research. I put just 4 examples here, just to make it quick. Just the Stannex. We know Stannex is we know what it is. Everybody knows what it is, what it was. But we know that specific for Stannex, it uses a PLC library from Siemens Semantic that is using that DLL to execute some commands and all that. We all know this story. So that the family used that as specific characteristics on that, right? So another one for from ZU or ZBot, which is the banking malware. There's a specific region in the file that has has been almost the same across multiple families. So you have actual characteristic out of that. Same goes for Dino, which is part of the Animal Farm, which is supposed to be a nation-state sponsor malware. And also from, I put an example of the Bangladesh hack, which the malware actually hooked into a DLL to be able to, patches the code and see the data transaction and that. So there are quite specific characteristics out of example those 4 that no matter what you do, you need to have those pieces of information, right? So imagine if you have a way to say, hey, I wanted to search for this particular thing and come out, results out of that, right? So just example, Stannex. Imagine again a way that you have, put just, Dino.exe and search that information out of a bunch of hashes. Again, imagine a way that you can put a section of the file and give you all these other malwares that matches that thing. And same goes for BB Swift for giving you all these files that have that reference. They are within the file, within the files itself, the reference text within the files. So that got us thinking, saying, wait, we can actually probably build a system to be able to achieve the research. We actually need to build a system, a framework to process the file in the way we think will get most value out of it. We're not just going to use like everybody like file-based hashes, which is easy to compute and faster. Everybody loves that. Everybody loves antivirus, like not going after behavior. It's faster than that. So we got us all these pieces thinking and say, wait, maybe we can build DNA. Well, wait, I'm gonna explain what DNA means for us. To search that whatever is information is being recovered out of those pattern and characteristics. So build a search profiling engine, but specific to the file type itself. When I mean file type, the P, the executables, has all the definitions, or all the possibilities that the file type defines. And there's hundreds of those possibilities. If you go for file type of Office file, like a Word file have a lot of all the definitions. How many pages they have, how many words, how many if there's a screenshot, and this is the size, this is the resolution. All those characteristics are within the file format, right? And on top of that, BERT built a search capability on those, on that data, rationalize, categorize all that data, so we can do at the very end a large-scale malware analytics, right? So we package all these files, defining the format, and we defining each of those interactions and each of those components in a very rational database format, so we can query that information and make it look better, right? So now we're gonna one other thing I want to show is not like if we go for P file format, we have all those definitions on the file format. The file headers, the sections, resources, certificate size, versions, import table and export table. But the way it look like this, I really don't want you to remember all this. I need you guys to picture something like this, right? Which I don't know, it's a piece of mortar. I've just Googled the first one, I pick it up. But imagine like a file, a malware, when you have all those small pieces that together, it makes it a whole thing, a whole working or operable thing. So why I will search for the entire thing when maybe I change one small piece, and of course it becomes a different hash, right? So an example of this is if this is a piece of a car, and I steal this car from you, and someone who steal your car painted in a different color, it's still your car. It's just painted a different way, right? So the concept goes like this. If we process all these, files, and we extract all the characteristics possible, maybe we can find better ways to do search and to do matching and to do clustering, which is what we did. So again, I don't want to see it like this. I want to more see you like this, like a whole set of pieces that come together to make a malware itself. So this is what we did. And to start to do a little bit analytics on all the rationalized information that we extract for each of the files we process, and we process 30 million files, malware. We start doing clustering on each of some of the files that we want to cluster. So in this case, is Duku. And this is actually very, very nice. Duku is supposed to be a nation-state malware, supposed to be for some big government in America, right? So we can see if out of one file, one data extraction, the first one, which is the red, we have another one that it looks the same. The clustering is the same. The size of the bubble is how big and what's the percentage of the similarity. And the others are the ones that have less percent of similarity from the father and goes like a spiral like that, right? So this is something really, really beautiful of this. This is the next chart, which is out of the father, right? We start searching percent of similarity, and at some point, actually by 34.7%. What is Duku? It becomes Stannex. It becomes the second version of Stannex. And then it continues all the way below. And this is code. This is not like me saying, oh, this is that. This is code. This is like functions, APIs, resources, all crammed together, scramble, getting in small pieces and comparing the father, which is Duku, against all the other ones, the ones we have in 30 million database set. So it could be that whoever built Stannex probably built Duku, or it could be that the programming almost in the same ways, almost using the same techniques, almost using the same APIs to be able to achieve that, right? An example like that is that two different pieces of two files that have a different hash value have the same API, probably have the same size and the same date, but of course they are different. They have some small piece that makes the two files being different. But for us, those two things are the same because it shares the same functions, resources, and some other thing. And this is just the driver for one of those supposed to be nation-state malware. So out of all this, we can get a lot more information out of the files, and that's the beauty of this, when you rationalize a lot of data and start making sense of that. And one of the things we thought about it, we want to find what's the worst day for the user in terms of malware activity. We say, okay, maybe we go for file-based time. We'll call it the worst day for users because a lot of malware being compiled in that day. Of course, we knew that malware authors, modifies the file stamp for the files, so we had to before doing the actual research, we say for sure it's going to be epoch equals 0, which is the first being modified, the timestamp to become 0, meaning it starts in the 70s, the 1st of January. So of course the malware authors will clean that data, and the majority of them will be like that, which we're wrong. And this is the beauty of this when you start processing data, is that the data, something you actually think is the data is actually telling you what it is in reality. So we say we got this, and the size of the bubbles are the size, how many, times are, that represent in the exercise, in the summary that we did of all the files. And right there you have a file, the majority of them, or like a huge majority of them, is like from 92. And we say, like, this is wrong. It's like really wrong somewhere. It's really wrong. The second one, it was epoch equals 0, which is what I believe. But it was wrong. We were very wrong. So what is that date? When we say, like, we started Googling, and we found that for 6 different versions of Delphi, the linker was actually put in the same timestamp. It was hard-coded in the linker that built the file. So we say, oh, that's it. It's the linker that living, and all those files seems to be, Delphi old versions. And again, the data is telling us something different than it was, in our mind. And we got this. We built another one. Is like we said, we're gonna cluster the same, absolutely same code. We determine, what the code section in the file, which is something a little bit complicated, but we make it simple. And we say, we're gonna cluster all the code that's actually being the same in the entire database set. And right there, we say we're gonna spot the family of CUs, then we're gonna spot the family of CBOT, we're gonna spot some of the families that well know as being sharing. Maybe the builder of the malware will actually, it will do a lazy job. It will just modify a piece of the file and not the entire thing, and it will cluster all that data. And we're terribly wrong. The thing we forgot are the actual installers. Nullsoft installer, like the install shield that is used now, or the 7-zip out extract, and some other, I think it's a Chinese installer somewhere. And again, something we thought about it, we forgot about installers. And then, again, the data is talking back to us and saying, you're wrong, what were you actually thinking? And we said, we want to determine, roughly out of the entire set, what's the actual, mean of the data in terms of percentage? What's the actual space out of it? And it turns out to be like 100K is the average for all the malware that we have. And since we process a lot of files, we had to have a table which grabs all the import table of all the files that we process, and have, what's the count for each of the API that is actually being used in the system. As you can see, out of the DLL, kernel 32 get proc address is 12 million times call within the files that we process. And we do this is actually very useful for something that I'm going to show you, I hope, right now. I hope it works. So you can see, we have, for each of the file process, we do a count, we put in there in the database, and we use this data to use it with some other connectors and produce, a better way to present data. So I give you an example. If we process a file that has been dumped in memory, all the import tables are absolutely broken. There's nothing you can do it. But still, the piece of text is within whatever you dump in memory. So if I know this piece of text is an API that I have it in my database, I can relate that this program is using this API. So again, of data that is not useful or not working because the executable doesn't work, you can still get meaningful information out of that. And now it's I'm gonna check this, see if it works. So we mentioned. And this is, I hope we're going to get beauty out of bad data. Imagine this, for each API, I put kind of the size that represents within the entire set. So that's, one of the 8 million function API. This is the build log. Imagine the size of the bubbles are the size of how many count it represents in the entire database set, right? So we have that, imagine that as, in a universe, this galaxy has this planet that is like, it's called virtual log in this case. So imagine that this is the beauty of touch, that we can actually zoom out and becomes, different planets. I'm still in the galaxy of kernel 32. Imagine all the other different galaxies that are actually out there. And this is starting to become, something, maybe I'm not expecting everybody to read it, but this is just kernel 32. Now if I move this way, I have user 32. And this is just 2 details. So imagine I zoom out, and I have more, and I have more, and more, and more, and more, and more, and everything. And this is like how it looks when you process 30 million files. Looks like a universe of function calls. Each bubble represents actual L, and each bubble represents, the size of all the colors is how many instance of that function is being called. So now we have actually spread the distribution for all the IPIs from malware that we process in a graph, and that's what we actually presented. So the beauty of this is a limited zoom. Sorry for that. The file is 80 megabyte. But the beauty of this is to find not the ones that are, not these ones, like everybody calls these ones. The beauty is finding like these ones, like the ones that, just a few people. And this is like a simple one, HTTP API. Or the ones, sorry, it's complicated. These ones, like maybe a typo somewhere. This NTU map section, or this one. With this, you can actually map, probably, a lot of all the different things. And this is like, where are these long? This is a typo. Libreria. Or create file in a different. This is a kernel 32 with a dot at the end, trying to masquerade the original one, right? So this is what it looks like when you process a lot of that. That's, again, the data is telling us, how it looks in a universe type. So let me go back to the presentation. We call it the universe of malware APIs. That's, some of the distributions for some of the DLs being called and some of that. And again, this is I've never seen a graphic like that before. So it looks, to me, it looks beauty out of like mess. It looks beauty out of that. So we talk about the research, but we say we built a software to do the research, and that's what we did. So we're going to talk a little bit of the architecture and some examples. So what I basically do is an engine, and there's a white hat guy there that has a portal, and out of that, the portal calls the APIs, and all the APIs is 182 different APIs as right now. You call those APIs to be able to get the data, push the data, or query the data. Basically, there's an API for each of the functions for each of the file format that we have in the data, in the system, the framework. And then when you submit something, it says, hey, this is the MIME type being, executable. It goes through the processors. The processor has his own plugin system that extracts each of the characteristics that each of the API, each of the processor plugin do. Like we have one plugin that extract, the strings, one plugin that extract, perform some other function like SSLD or different strings that process do, and you can actually add that, and you can actually modify the code to whatever you want and add your own processor or your own plugin. So you want to do, I don't know, you like to do flaws, which is a new tool now, and just code being able to execute flaws for each of the file when it matches the MIME type. You can just do that, and that goes to the codex search engine, and all that the rational information gets spread through different MongoDB database set or collections, if you want to prefer like that, where we store the samples and we store the metadata that we extract for each of the samples, and we store the versioning of the plugins. So we do that because maybe you develop one plugin and then you forgot something, you want to modify the plugin, you upgrade the version, and you need to execute only just that plugin across the entire database set. So out of that, in a different section is the actual web portal, where you're going to see a few examples in a minute. So out of that, all this code get being executed and give you the data in a rational way that you can have. So basically, with that rational information, you can do malware comparison, for each of the metadata items that we extract for each one of them, and you can do accurate comparison by each of the single pieces. So if you build a similarity base with the system, you can actually, if you say this file, you run similarity and it's equal as this for whatever reason, or you have this piece, you can just select one or two of the files and you create automatically a rule out of that. So you're hunting for a family, you just select the files if you get the files, and you can build maybe a rule that will actually protect you for that given family if it stays the way it stays in a normal pattern like that. And of course, they bring you what we call it the analyst panel, which is a website with 150 different searchable index items out of each file. So the technology that's behind is we use GridFS for storage of the file. We use Mongo. Well, it's running on Ubuntu. The web is Angular. We use D3 for the graphics, all those bubbles that you saw. We use, of course, Docker for easy implementation, easy deployment and implementation. It's all coded in Python that you can actually go there and just do whatever with the code. We use Battle as the API, and at the very end, we use Apache. So I want to show you some of the examples that we just put together. So in this case, one of the data that we can actually get out of the files are, the signed certificate code that's within the file. So if someone steals a certificate and you process the file that has the certificate serial number, in this case, this is a search for Duku2 actually. If you know the certificate thumbprint serial number, you can just put the certificate thumbprint serial number, and it will search for that and will bring you that information that is there, which is the Duku. Same thing where you know a file that he himself reveals a specific name. In this case, it's a malware call from the family called SAMAS. You can search, hey, give me all the files that has a version string in the parameter file name, which is again a characteristic of the P file with the specific name. Just give me all of that. So we're not talking about hashes and talking about anything like that. We're just talking specific characteristics out of files. Give me all of that. So again, we're trying to walk away from file-based hash and going after characteristics. And another one here, you read this amazing research for ESET, or at that given time was for Symantec. You say, Statnex is using these functions to hook into the process for each of the process being executed, and is using these APIs you can search for, hey, give me executables that this piece of strings that we know is an API that is not referenced in the import table, so we know this piece of string within the file. Give me all of that, and tell me, well, give me all of that has the match. And the match is this string with that particular name that is not referenced in the import table. And you have right there is 103 different versions of Starnex, different files, different hashes, if you want to call it in that way. So we put, all this, we make it, the interface, we make it as easy as possible to malware hunters to use it to start processing files. And to be able to achieve that, we have private access to some of the largest malware database set, part of the work we do for this case, Deloitte. And so what we did is there's a place called APT Notes, which collects all the reports from different APT actors across the years. It has 11 years right now of APT actors. And we got all the hashes, all the files, not the hashes, all the files. We got all the hashes from those reports, and we collect all those files for all those reports, and we put it we zip it, put it in a file, and we upload it to our Git, so everybody can actually download it. There's 7,000 files. I start processing those files, which is just a click and load, and that's it. You process the file. It takes time, of course, and you can start searching and doing some stuff for comparing files for malware actors, APT actors that are being known. The beauty of this, of course, is open source. Again, this started as a research, and we encountered that there was nothing quite like it the way we wanted, and well, we had to build it, and might as well just share it to the world so people can process file, process malware, or process sometimes good files to determine what is all the files malware. When I say process good files, an example for the Bangladesh hack, we had the file. We had the Bangladesh malware, and we knew that we had the file because we searched for the regional DLL, because within our system, it seems that someone actually uploaded some of the Swift DLL files. So we knew the names of the API being called by the malware, and we put those names, and hey, the malware, it was there. So again, you can go there, clone it. If you want to help, just help. We'll need a lot of help and make it better. Please, let's help us to make it better. And I think I have a few minutes. We create also a Twitter account. So you can, over there, you can ask one of us to provide the APT password for the zip file that contains roughly 7,000 malware. We just don't give it away because it's kind of dangerous. So you direct message me or whoever in the team will give you the password. And if you want to follow the Twitter, we post sometimes we do malware similarity. So last week there was a malware attack from I think the people from Symantec. It was called ODNAF or something like that. I don't remember now. So they turned out that some of the files that we process within our database, we actually have more than the actual report from Symantec. And that's actually, we say, wait, this is kind of strange. How come this guy had more? It's because sometimes we have files that some other vendor doesn't have. If Symantec, it doesn't have all the spreads across the world. It's not just them, it's everybody in the antivirus industry. So if they don't see a file, they cannot cluster the file in the same way that we do. Sometimes we get lucky and we have one file that they don't have. So we send, I say, hey, this one has this % of similarity. You want this, you have the file, do the clustering again, and maybe you have one more hash to be published in the website. So we do that again for free. We just there's no one. We just do this for our clients. So again, this is the Twitter account, and if you have questions, I would love to hear that. I'm sure I don't have all the answers, but I will try. So thank you.
Questions?
Thank you.
Thanks for the talk. You talk about IARA rules generation.
Yep.
When we select multiple malwares, do you try to generate the minimum set of rules, or do you just generate a wide array of rules that will catch everything, but that are not maybe the minimum set?
We didn't want to reinvent the rules, so we use Jarhan. So that uses, has 400 megabyte database of known APIs. So discard all that. It goes after some of the strings, even in Unicode, and also do code comparison. So you might have, depends on the file that you want to compare, what they call it a super rule, a rule that matches a certain type, certain files, or a YARA rule that matches 1 or 2 or probably even 1. So that's the 2 ways. In the future, we think we're gonna do our own YARA rule generation in terms of the same search patterns that you put within the system, and you can run it across the entire system. So at least in 30 million, you're not gonna have false positive. But as right now, we use Jarhan, which is for the ones we test, is the best one. There are some certain limitations there too. Sorry. In the Twitter on the Git, to make it everybody life easier, and you want to do Docker, which is build VMware and VirtualBox. So you just download the VM, just run files, copy the files there, and start hunting. We want, again, help the hunters with more tools. So that's it. Any other questions?
Time for a few more questions, if anyone else have one.
Sorry if I make it too fast.
You did fine. Okay, seems we're out of questions, so thank you very much.
Thank you.